Eu sei que é absurdo pensar hoje, mas ter uma nuvem acoplada ao nosso cérebro poderia ser uma solução muito, muito desejada por mim. A2AI é uma associação nova, uma iniciativa que foi criada pelo meu irmão, e eu sigo pela paixão de tecnologia, por acreditar no futuro, no desenvolvimento.
Quando criei a I2AI, a ideia era justamente essa, de colocar essas pessoas que acreditam que a tecnologia pode criar um mundo melhor para conversar, para aprender, para desenhar esse mundo. A gente conversando, empresas de tecnologia com empresas líderes nos seus segmentos, empreendedores com investidores, pesquisadores com os empreendedores, tudo isso pode criar um mundo muito melhor.
Às vezes eu penso na quantidade de mudanças que temos no nosso dia a dia, na quantidade de informações e nas possibilidades incríveis que a tecnologia está trilhando para o nosso futuro.
Eu nunca deixei de olhar para o mundo de tecnologia e ver as novidades acontecendo no mercado. Eu vi a parte de inteligência artificial e nos últimos anos a inteligência artificial começou a ser algo que podia mudar muito a realidade das empresas.
Inteligência artificial é uma tecnologia que dá capacidade para as máquinas aprenderem como um humano.
Ela pode ajudar você a escolher melhores filmes que você gosta, ou pode ajudar os médicos a combaterem mais rapidamente, mais assertivamente o câncer, ou nas empresas reduzir desperdício.
Quando eu olho para o nosso país, vejo que temos muito para avançar, tanto na adoção de tecnologia, como em educação e incentivo às iniciativas de desenvolvimento.
Eu vi a tecnologia se transformar no que ela é hoje. Eu vejo a inteligência artificial e vejo o que ela pode fazer para as empresas. É algo, para mim, fantástico.
Inteligência artificial já é uma realidade. Se você quer acompanhar esse movimento, siga a I2AI, uma associação com o propósito de desenvolver todas as pontas do ecossistema.
A EducaCross é a experiência de aprendizagem que está revolucionando a educação. De maneira ativa, divertida e significativa, foi pensada e desenvolvida para promover a interação entre professores, escola, alunos e famílias. Projetada para a educação infantil e o ensino fundamental 1, oferece experiências variadas a cada ator do processo educacional. Os jogos digitais são instrumentos poderosos para desenvolver o protagonismo do aluno de forma lúdica, significativa e autônoma. Com tecnologia de ponta e inteligência artificial, cada criança aprende no seu melhor ritmo. A EducaCross é reconhecida e premiada pelas maiores instituições do Brasil e também no exterior. Todos os jogos são mapeados pela BNCC e apresentam orientações pedagógicas. O professor acessa um conjunto de jogos semanais que dialogam com seu material didático ao longo do ano escolar, além de informações sobre o desempenho dos alunos em tempo real e contínuo. O professor também pode criar missões para um aluno, grupo ou para a turma toda. Ah, e dá para escolher se as atividades serão em português ou inglês. Os jogos podem ser aplicados em salas de aula, laboratórios de informática, em casa e em horários alternados para escolas de período integral. É ensinar e aprender de maneira tecnológica em qualquer situação. Nossa fábrica de games não para. São milhares de jogos disponíveis e milhares de vidas impactadas. Por meio da plataforma, os gestores têm uma visão geral, com dados detalhados, relatórios individualizados e suporte exclusivo. As famílias podem interagir, acompanhar o desenvolvimento das crianças e incentivar o aprendizado. A EducaCross possui muitos amigos, parceiros e educalovers, todos juntos por uma educação transformadora. Faça como nossas escolas parceiras em todo o Brasil e transforme o ensino e aprendizagem numa jornada interessante, gamificada, com alunos engajados e motivados. EducaCross, aprendizagem inteligente e divertida.
Bom dia, pessoal. Tudo bem? Eu sou Wagner Santos, CDO da I2AI, E vamos então para o nosso último dia do AI Experience. Começamos então, vamos fazer rapidamente aquela nossa apresentação institucional, né? Somos a i2AI, somos a associação sem fins lucrativos que visa promover o desenvolvimento da inteligência artificial, né? O ecossistema da inteligência artificial no Brasil, na América do Sul e, por que não, no mundo. Nosso objetivo é unir as diferentes pontas desse ecossistema, então desde profissionais, o governo, universidades, institutos de pesquisa, empresas, startup, empresas de grande porte. A gente entende que a inteligência artificial ela é transformadora para todos esses players e é importante, então, realmente, né, trazê-los juntos, que a gente consiga fomentar e fazer com que esse ambiente seja o mais rico possível. Para quem não conhece, então, a i2AI, nós encorajamos as pessoas a entrar no nosso site e se associarem conosco. Temos cursos, temos eventos de networking, comitês de setores específicos, como o varejo, educação. E promovemos eventos ao longo do ano. Tivemos já, né, o simpósio de inteligência artificial, hoje é o AI Experience, e teremos aí em breve o AI Journey e o i2AI Awards ainda este ano. A dinâmica, né, para quem aí não teve a chance de assistir aí nos outros dias, né, então a dinâmica do AI Experience, nós então iniciamos aí, né, um pouco antes do meio-dia, fazemos um warm-up com um entrevistador, onde discutimos aquilo que vai ser falado. Ao meio-dia trazemos o entrevistado e à noite, às 19h30, fazemos uma mesa redonda discutindo aquela entrevista e os assuntos relacionados àquele tema. O nosso evento tem o patrocínio importantíssimo da EducaCross e o apoio do Cantarino Brasileiro, a Lean Sales, a Solos IT e a PUC de Campinas. Aí está, né, essa programação que tivemos nos dias anteriores. Esse conteúdo está disponível no YouTube para vocês assistirem, tanto as entrevistas como a mesa redonda que aconteceu no período noturno. Então, para quem não pôde acompanhar ao vivo, temos o nosso canal no YouTube. A entrevista segunda-feira, onde a gente falou sobre inteligência artificial e a China, basicamente, uma entrevista com Brian Tsei. O futuro da IA, o futuro da educação com a inteligência artificial, uma entrevista com Jordan Rosiak. O IA e o futuro do trabalho com o Gary Bowles. Ontem tivemos a IA e ética com o Domingo Farinha e o Ricardo Raposo. E hoje vamos falar de IA neurosimbólica ou Neurosymbolic AI. Vamos entrevistar o Luiz Lamb. Teremos como entrevistador o Bruno Gomes. Aproveitando esta deixa, vamos então trazer o Bruno conosco. Tudo bem, Bruno? Bom dia.
Tudo bem, bom dia. Nesse ponto é em português, né? Por enquanto.
Sim. Vamos nesse ponto. Eu esqueci de falar isso, bem lembrado. As entrevistas, como vocês viram, né, e trouxemos referências internacionais, elas acontecem, elas são feitas em inglês a partir do meio-dia, e temos a mesa redonda para discutir, né, em português aquilo que foi falado na entrevista. Então vamos lá, Bruno. Daqui a pouco vamos trazer o Luiz Lamb. Mas já preparando até para as pessoas conhecerem, né? Então também sou cientista de dados, né? Trabalho já na área há um tempo. O que é a IA neurosimbólica? Para as pessoas começarem a localizar o assunto antes da conversa com o Luiz.
Tá, eu não posso estragar a surpresa, o Luiz vai dar a definição perfeita, provavelmente. Mas, e também a AI neurosimbólica não é a minha área, eu tangencio a AI neurosimbólica, mas por causa desse evento, inclusive, eu fui ler, por causa do evento, eu fui ler algumas coisas, inclusive ler completamente o artigo do Luiz, um excelente artigo, Neurosymbolic AI, The Third Wave. Acho que todo mundo deveria ler esse artigo, um artigo que é praticamente um mini tratado sobre AI neurosimbólica. E a AI neurosimbólica você une o que já é conhecido de arquitetura neural com um pouquinho da velha AI. Assim, é meio simplista dizer isso, porque não é exatamente igual à velha AI. Você tem, na verdade, uma contextualização do que se usava antigamente em AI, baseada na lógica, junto com o que se usa hoje de abordagem conexionista usando as redes neurais. Não exclusivamente redes neurais, tá? Apesar de que é o que é mais famoso hoje em dia, as abordagens que mais deram certo em indústria são o aprendizado profundo usando redes neurais. Mas, por exemplo, árvores de decisão são algoritmos de inteligência artificial neurosimbólica por natureza.
E as árvores de decisão, elas são utilizadas, né, também diria, né, as coisas que mais dão resultados, se você for olhar em dados não estruturados, né, falar imagens, texto, áudio, onde tem as redes neurais, e com dados tabulares, dados estruturados, o que, né, as pessoas acabam extraindo os melhores resultados são os algoritmos, né, de ensembles, e que são baseados em árvores também, no final das contas, né? Todas as coisas meio que se unem em última instância. Puder falar um pouquinho de você, então, Bruno, sua trajetória aí no Data Science, inteligência artificial?
Obrigado. Pessoal, eu sou Bruno Duarte Gomes, eu sou neurocientista de formação e trabalhando com neurociência, na verdade, isso me levou a trabalhar com inteligência artificial. Eu acho que hoje em dia é meio que como uma consequência um pouco natural, ao menos a vontade, eu acho que todo neurocientista tem, de trabalhar com inteligência artificial, especialmente os neurocientistas que trabalham com os aspectos de o que a gente chama de biofísica de sistemas em neurociência, que é você tentar estudar os aspectos realmente funcionais do cérebro. Eu vejo muita gente que trabalha com eletrofisiologia e neurociência, tentando trabalhar com inteligência artificial. Isso é bem menos frequente quando você considera o pessoal de neuroquímica, por exemplo. Eu vejo que isso acontece porque quem trabalha com eletrofisiologia e neurociência tem sempre uma iniciação, um aporte matemático interessante. Aí, a migração ou a interseção com a inteligência artificial é mais fácil de acontecer. Então, eu trabalhava com eletrofisiologia, sempre trabalhei com eletrofisiologia. Desde a minha formação aqui em Belém do Pará, eu fiz a pós-graduação aqui em Belém mesmo, com o grande Luiz Carlos de Lima Silveira, que já é faleceu em 2016. E a abordagem que o Luiz Carlos de Lima Silveira proporcionava para nós, pós-graduandos daquela época, era sempre de interface, né? Então, uma interface neurociência e computação. Na época, inteligência artificial, a gente nem falava nisso, na época da minha pós-graduação. Mas sempre tinha uma interface neurociência matemática. Ele estava muito interessado nos aspectos quantitativos que poderiam descrever essa ou aquela propriedade do cérebro. Era isso que o laboratório dele fazia, tudo focado no sistema visual, na visão. E aí eu entrei no laboratório do Luiz Silveira, e aí eu me apaixonei por essa parte um pouco mais quantitativa e decidi seguir nessa área. Em 2014 eu fui para o MIT fazer um pós-doutorado, fiquei 2 anos e meio, e de modo interessante, eu sempre conto esse caso por aí, em 2015, no início de 2015, apareceu um pesquisador lá no MIT para dar uma palestra, ninguém ligou muito não, mas eu fui lá ver. Esse cara era o Geoffrey Hinton.
Geoffrey Hinton que vocês estão... Só o Geoffrey Hinton.
Só o Geoffrey Hinton. Então, naquela época, ele não era ainda muito famoso, ele já era muito famoso dentro do aprendizado de máquina, dentro das pessoas que já estavam empolgadas com o artigo de 2012 da LexNet. Então, claro que ele já era famoso, apareceram principalmente as pessoas de computação, poucas pessoas de neurociência foram ver a palestra dele. Eu fiquei na primeira fila, e foi quando eu conheci o Geoffrey Hinton, assistindo uma palestra dele na primeira fila de MIT, e a palestra foi espetacular. As perguntas foram muito interessantes, ele estava explicando como é que o sistema visual trabalhava com invariância, translação. Essa era uma preocupação dele naquela época. E naquela época, inclusive, curiosamente, ele já estava chateado com o tal do pooling. Por que o Geoffrey Hinton estava chateado com o tal do pooling para trabalhar com invariância e translação? Porque o cérebro não faz isso. Presta atenção. O Geoffrey Hinton, ele sempre está chateado com o que quer que dê certo em machine learning, porque o cérebro não faz isso. Não sei se vocês já ouviram falar, mas o Geoffrey Hinton começou a carreira como neurocientista, né? Aliás, começou como neuropsicólogo, e aí, então, ele foi depois para a inteligência artificial. Isso é estimulante, inclusive, para quem é neurocientista, né? Ouvir um negócio desse.
Né? E é um dos grandes papas, né, das redes neurais, de tudo, né? Toda essa revolução que veio, ele é um dos mais importantes, sem dúvidas.
Então, foi assim que eu fui caindo em inteligência artificial, aí comecei a utilizar a inteligência artificial para processar dados de neurociência, e agora é que eu estou começando algumas abordagens em AI pura, e tentando fazer uma abordagem Brain Spiral, junto com colegas ainda do MIT e com um colega da Europa. Né? A gente está iniciando essa abordagem aí. E uma área que eu acho bem interessante em inteligência artificial, ainda a neurosimbólica, que eu acho que vai tomar a inteligência artificial de assalto. Vamos ver se o Luiz, claro que o Luiz deve concordar com isso, o Luiz Lamb, vamos ter entrevista depois. Outra área que eu acho muito interessante é a interseção sistemas dinâmicos e inteligência artificial. Aí você entra naquela seara, inclusive, de Physics Informed Machine Learning, ou Physics Informed Deep Learning, que é o Deep Learning que se chama Under Physical Constraints, é o Deep Learning cujas funções objetivas são limitadas por parâmetros físicos, da física, não estou falando da ciência física.
Uhum.
Então, isso é muito interessante, porque dentro da neurociência tem um papel central. Tudo que eu procuro, na verdade, inteligência artificial, eu tento colocar dentro da neurociência. Então, eu acho que essa
com
parte...
link, né?
Sempre com link. A parte de Physics Informed Machine Learning, junto com o que a gente chama de sistemas dinâmicos voltados a dados, que é Data Driven Dynamical Systems, é uma coisa que vai ter um grande efeito em neurociência nos próximos anos. Com a AI neurosimbólica, eu consigo ver um link, inclusive fazendo uma ligação entre atividade cerebral e comportamento, mas eu vou deixar para o Luiz.
Vamos trazer o Luiz, então, sem mais delongas. Ele já vai entrar aí conosco, está nos bastidores. Bom dia, good morning, Luiz. Tudo bem?
Tudo bem.
English. Muito obrigado pela presença. Vou deixar vocês dois, então, à vontade. Obrigado, tanto Bruno e Luiz, pela presença, pela entrevista. Fiquem à vontade.
Thank you, Wagner. If you are not understanding us now, you are. So it's really a privilege to have the opportunity to interview Luiz Lamb. If you've been reading the top discussions in AI over the last maybe 2 or 3 years, you've heard about Luiz. So Luiz, good to have you here. It's a pleasure.
It's an honor, Bruno. It's so great to be with you. Thank you so much for your invitation.
Cool. Luiz, you work with, of course, neurosymbolic AI, but it's said that you work with integrated machine learning reasoning in general, but in also AI ethics and social computing, innovation, strategy, and technology management. Luiz, guys, is a professor in the Universidade Federal do Rio Grande do Sul in Brazil. But incidentally, speaking about technology management, I think you are now in Boston, right? You are working in the MIT Sloan School of Management?
Yes, I am at the moment at the Legatum Center for Development and Entrepreneurship. And I'm working on helping the fellows to build innovation-driven startups in growth markets. So we have fellows that are more experienced. We have student fellows that are trying to build their projects and transform them into businesses, and many of those projects are focused on AI. So I'm helping people to transform AI into economic impact that helps developing, the developing regions of the country, of the world, or let's say the growth markets is the best terminology to refer to our countries that are growing at a faster rate in the developing regions. And I'm currently working on that over here at MIT.
Cool, great. You are in Boston, the best season of the year, by the way, autumn. Oh, Boston is great in autumn. I miss that place. So, Luiz, I have a few questions. I think, Jefferson told me that we can open to the audience at some point. And if you are hearing me well, at some point, I will open to your questions. And then if you want to write down your questions in Portuguese, I can translate to English, and then we ask Luiz. According to time, we always have a restriction in time, you know that. According to the time restriction that we might have, I will select a few questions, okay? Just a few questions of who knows. So let's start simple I think it's simple. Probably I've tried to select questions, Luis, that could be important. That might be important for the audience, not for myself. But the last questions, just that I consider maybe important for me and to the whole audience. So the first question would be, what are the fundamental building blocks? I mean, the necessary and sufficient ingredients of neurosymbolic AI.
So that's a great question. In neurosymbolic AI, what we do is to use the two paradigms of AI in a hybrid way, in a harmonic way. Just to give an example, Daniel Kahneman, who's a cognitive psychologist and economist who won the Nobel Prize for Economics, he has his theory of cognitive reasoning and cognitive psychology that he developed over 40 years with Tversky. And in some part of his theory, he has these distinctions between system 1 and system 2. System 1, that's very fast, that is reactive to what we see in the environment. For instance, when I see you, and I've seen you many times, I instantly recognize you. I know it's Bruno, right? Or when I'm crossing the street, I've been trained many times over the last decades or early on in infancy, I immediately react to any danger. For instance, a car coming very fast. So this is a kind of reactive reasoning that is learned over the first years of our lives. And as we acquire more and more experience, we become very aware of the situation around us in the environment. I'm not going to use very technical language to make things very clear. So this is system 1, very reactive, very quick. And system 2 is something that we are also endowed with, and Kahneman says that it's a more reflexive system that we have in our cognition, that when we see new situations, when we are in critical situations, we reason, we refer to prior knowledge that is not automated, we gather information from the system, and then we build a new theory about how to react. Let's make a very simple analogy here. When we're going to work every day, you learn the way to your work, by heart. You don't even think about, changing gears in the car. You learn to drive. You don't even think to go to work because you did that many, many times. Whereas if you go to a new city where you're doing, say, you are going on a trip, on vacation, on our holidays, then what you do, you have to learn about the environment. You cannot start walking randomly in the city, for instance, to go to the conference center to attend a talk. Then you have to build knowledge and you have to reason about this new situation. Then you are using what we say is the system 2 of cognition. Or when you are dealing with new information, you use the best of your cognition to build a new theory about the environment, then to react in this environment and succeed in your goals. So in neurosymbolic AI, we have this analogy. We have this very fast machine learning algorithms like deep neural networks that do extremely good pattern recognition and correlations and associations of previously seen data that is labeled. And then when you see when you provide a new set of data, new set of images, the algorithm is very fast. However, this kind of approach doesn't work for everything. When you have a critical system, when you have applications that are sensitive, you have to reflect upon. You cannot use these systems automatically. You have to reason about these very complex scenarios. For instance, if you are doing a system where you have to provide guarantees to people, say like in the aero industry, you wouldn't go into an airplane that has a safety level of 95%, because it means that maybe in 5% of the cases you would have accidents. For some certain applications, or if you are using or if you're controlling a nuclear power engine, or if you are controlling something that's very sensitive, you need assurances. You cannot be imprecise. You cannot run risks. So the best way to approach this kind of systems is by using a logic-based approach, a symbolic approach. And by logic approach, we mean the way that mathematicians and computer scientists, they use to formalize, the computational constructions or mathematical proofs, or the way we formalize reasoning. Why? Because in certain applications, in certain scenarios, you need almost perfect guarantees to deploy certain technologies. It's okay if when we are using our mobile phones and today this is automatic. They ask us, well, is this person, your friend John, that I have all these previously labeled pictures? Is this person John? And you say, okay, I have 100 pictures of John, and then the next 3 or 5 there is a wrong label. Okay, let's say, wow, 2-3%, it's okay, it's a mistake. Now imagine if you go into an airplane, you think, wow, the airplane will reach the destination with 95% probability. Do you go into that airplane? I don't think so. So, or if you consider that you have a nuclear power engine in certain places of the world, and would you be safe living in close to a nuclear power engine or nuclear power station that operates safely in 99% of the cases? I don't think so. So, and other things that this is just to give an example of very critical applications, but in other scenarios, this is also very important. For instance, if you are developing a computer chip for machine learning, like an integrated circuit for machine learning, you want to make sure that this integrated circuit, that's called chips these days, that they operate like almost 100% of the time in a proper way. So you use neurosymbolic approaches when you have to guarantee that the behavior of the system will satisfy certain quality requirements, certain safety requirements, certain security requirements. And the nice thing, the beautiful thing here, Bruno, and as you are a researcher of, I say, a researcher of the brain. If you're a cognitive psychologist or a cognitive science or a neuroscientist, you are always studying how the mind and brain works. The beauty here is that this approach of neurosymbolic AI, it fits very nicely with current theories of cognitive science and cognitive psychology, like the theory that developed by Daniel Kahneman and many people around the world, of course. Because reasoning is not only about pattern recognition, is not only about classifying massive amounts of data. Reasoning can be performed by agents, by humans, by observing smaller amounts of data and building new hypotheses and building a theory of reasoning. So the idea here is to combine the speed, the efficiency, the results that we have in neural networks with the approaches that are brought and studied by logicians, by computer scientists, by mathematicians, that provide us safe logical reasoning, safe inferences in critical situations and in applications that are very sensitive. So the neurosymbolic AI approach, for just giving some technological examples that I gave here, it's something that can offer you more safety, security, and guarantees in critical applications, but it's also a fit to a much more evolved theory of how human cognition works. So we combine artificial neural networks learning and logical reasoning into the same framework.
Yes, this is great. Something I was wondering yesterday, like I was reading in your paper, the neurosymbolic AI third wave, is that in psychology in the 80s, in the 70s and 80s, there was a view called computationalism. It was very prominent, and the view was you can describe the various layers of the psychological phenomena using logic and computational logic, of course. And there will be a way out of wait for the guys to know how the brain works so we can have a full description of cognition through psychology. It was a kind of a dominant view in some very important circles in the 80s and 70s. And what I'm seeing now is that it's something like similar. So with the neurosymbolic, I was also wondering, as a neuroscientist, of course, I was thinking that neurosymbolic AI could be maybe even a bridge between the natural neural responses and behavior. But if you can describe behavior in a logical way, and you can describe, we can have a better link between brain working and behavior. We are getting out a bit of the of the theme, but I can't resist. Okay, let's go to the next question. Because I have a list of questions for you, by the way. Okay, about logic, Luis. Logic has many layers, right? So some logic frameworks are more expressive than others. What is the main logical paradigm used in neurosymbolic AI? Is it the propositional logic? Is it first order logic? Can you talk a bit about that?
Yes, it's actually it's not only classical logic or non-classical logics. Actually, depending on the application, for instance, if you want to model something that you need to consider the variable time, or if you need to consider space, you have other logics that are appropriate to describe the situations, to specify and build proofs and building algorithms to reason about time, reasoning about knowledge, reasoning about probability, reasoning about many dimensions that we see in the world. Initially, logic was developed to represent mathematical reasoning, right? And this logic that is used to represent mathematical reasoning, to describe proofs in mathematics, to formalize mathematics, is known as classical logic. It stems out of the Greek tradition and goes through Frege, Boole, Russell, Gödel, those researchers, and they built this framework to represent mathematical knowledge, right? So what people realized, of course, it's not very recent, but in the past, logic was also used to describe human relations and human behavior, and even to describe logical systems that are connected to legal systems. Because if you think about any legislation, any systems of rules, those systems, those systematizations that lawyers and legislators use, they are a logical system. They're under a logical framework. They start from a set of premises, and from those set of premises and beliefs that we have in society that represent our cultural beliefs about our country, or about how people relate to each other in our country, we develop a system of rules that's a kind of logical system that represents the norms in terms of legal behavior. So this is kind of a more classical way of viewing logic. So classical logic was used to represent human knowledge and to represent legislation and rules. And also the key success of logic was in mathematics, the field of mathematical logic. You have prominent figures like Bertrand Russell, Frege, Kurt Gödel, and all those people who developed this theory. However, in the last century, and computer science have had a great influence, and also the field of linguistics and cognitive science, we started to realize that logic is a very good way of expressing precisely scientific reasoning, precisely scientific phenomena, precisely computational constructions. So logic was developed in a tradition that led to computational logic, and computational logic expressed the way that computers behave when they are performing computations, when they are executing algorithms. And in this sense, and considering all that happened in computer science and the role of computers these days, many logical systems were developed to express and represent and to analyze and to understand how computers work, how our intelligence, how our artificial intelligence or artificial intelligence mechanisms can be described. So today you have logics that describe probabilistic reasoning, logics that describe uncertainty, logics that describe multiple futures, linear future, logics that describe the past in relation to the future. Those are all temporal logics. You also have logics that describe our beliefs. For instance, when you have a belief system, for instance, if you are building an artificial intelligence system, you can have multiple agents that have different beliefs about the world. You can also use logics to describe the knowledge of agents, or the knowledge of the components that interact in a system. When we are interacting in a multi-agent system, in a system that's highly complex, if you take the web, there are logics that were developed to describe the behavior of people interacting with each other using computational systems. So we have this tradition of classical logics that was developed and had a lot of success in mathematics, and we have this tradition of non-classical logics that includes other dimensions of not only our behavior, but dimensions of life. You describe space, you describe time combined with space. You describe time combined with probability, combined with space. Of course, this becomes a very complex system. But what my point is that there are many logics that are used to describe different phenomena. If the key variable is how the computational system evolves in time, so you use a temporal logic to represent this phenomena. That's just to give an example.
Okay, thank you. We are so used to use in using computers that sometimes we forget that everything that you can run in a computer. Um, I'm saying that in case there's anyone like myself that had some difficulty thinking about logic as a good way to knowledge representation. But we are so used to run computers and that we forget that everything that we do in computers, from simulating complex equations uh, to for climate forecasts, to simulate brains, neurons, anything that you can do in computers is ultimately a nested chain of propositional logic. So this is amazing, right? So logic is really a good tool for knowledge representation.
Yeah, that's a good point. Knowledge representation is a very important field, Bruno. Well, very well spot, because people don't realize that in order to do any computation, for instance, if we want to add numbers in a computer, you must have a proper representation for that computer to run the calculations. The
Yeah.
same way, when you see, wow, the computer is seeing my pictures. No, no, no. The computer actually don't see a picture. There is a representation of the images in the computer. That's even not very exciting, because when you see that the way that you represent pictures in a computer, you realize, oh, you just see, this codification in this big, let's simplify things, these big matrices, that are either a binary representation or RGB or whatever codification. Wow, this is so boring. So the computer doesn't see the image. No, it doesn't. So knowledge representation and representation about the world is an extremely important field, because it's the way of finding the proper language or the proper way of representing some information that can be visual, can be a sign, can be a language, can be, the sound of our voice, can be music. Knowledge representation is the field that analyzes the best way, the best abstraction that we say, the best language, so that information is represented in a computer or in a data set that's going to be processed by a computer. And typically this translation into a representation mechanism, some people get surprised. When you're not used to computers, you get surprised that some of these things are, highly complex. Some of these things are kind of, not very interesting. And many of these translations, in the end of the day, that you do either an embedding or a matrix representation, or doesn't matter the name. So the knowledge representation is the way that you represent information, so that you can develop a smart algorithm or an artificial intelligence application. But knowledge representation is the way you represent information so that the computer can process this information. And in AI, we call this field knowledge representation and reasoning, because depending on the representation, you develop a proper reasoning system that is a set of algorithms that will perform inferences or calculations or operations over this knowledge that was represented by a language, by a certain way that's more convenient for the computers to process, to understand, and to analyze this information in a more efficient way. Because we are, as a species, human beings are obsessed with efficiency, with saving time, with running things very fast. So the essence of knowledge representation is to find the best way to represent certain kinds of data, and then to perform effective and efficient calculations with a computer.
Yeah. Luis, is it correct if I state that when you integrate the symbolic approach with neural networks, then you would have less uncertainty in the whole algorithm compared to when you use just neural networks?
Yeah, this
When I
is
say,
one of the. Yeah, sorry.
it's okay.
No, go on.
Yeah,
Go
when I say uncertainty, I mean even if you have when you say you have a high accuracy neural network working, of course, each time you run the neural network, even though the accuracy continues to be good, it will be different every time at each run. So you always have an uncertainty, even if your algorithm, your neural network is working well. But so when I integrate the symbolic approach together with this neural network, I would have a reduction in this uncertainty. Is it correct if I say that?
Well, this is one thing. This is one of the aims. When you are using a machine learning system that's purely a neural network based system, or any other system that deals with identifying correlations, identifying certain relations between data. You have certain limitations in the kind of precision you can reach, right? So it's a statistical approach, and you know what statistic means. So it doesn't mean that you have 100% accuracy in what you're doing, right? So there are several challenges that we still have in machine learning, and those challenges are connected to what you mentioned. For instance, the question of interpretability. How can we create an AI system where we can find the reasons, the explanations for the recommendations and for the inferences that the system generated? So how to interpret the system? So neurosymbolic AI brings a solution, because logical systems by construction, they must have not only a way of manipulating symbols, but they have the meaning associated with that symbol manipulation, which is the semantics associated with the logical system. That's a formal semantics. So in order to build systems that are interpretable, that are explainable, and also that are transparent, because sometimes one cannot explain why a machine learning system reached some output because of the complexity of those systems. This is something that building an integrated system that brings together the logical tradition of AI, where everything is explainable and you know exactly why the inferences took place, why the system produced certain results. Then by connecting those two schools, we can perhaps, we can build systems that are interpretable, that are, verifiable, that you can find reasons to identify why the system was not fair, why the system showed some biases. You can also build systems that are more secure. We cannot forget as well that those systems today, since the economy has moved to the digital world, we have certain security issues. We have vulnerabilities to cyber attacks and so on. We have questions of privacy. How can we maintain privacy of the data sets? So all those systems that we have today, those very powerful systems that brought us here to the popularity of AI, are systems that still have some limitations, that we have to identify the proper way of dealing with that. One of the things, and other two things that people say, not only with respect to fairness and to bias, for instance, people are very concerned about the transparency, that is how to explain why the system works, with misinformation, why the system generates misinformation is because the system doesn't have a proper semantics, doesn't have a proper understanding of how the world works. Right? It's a system based on data analysis, data crunching, and massive amount of data, but it doesn't have a formal semantics, a formal grounding with reality in terms of building a model of the world. So this is very important research issues, and this has led to many countries to try and regulate the use of AI. But to regulate the use of AI, we need to have technical systems or technical approach that can be built that provide explanations, that provide transparency, that provide interpretability for those systems so that they become more secure and they can be deployed in a safer way.
This is very interesting. One thing you said that close to reality. I'm realizing now that maybe when you integrate a neurosymbolic, when you have the neurosymbolic AI, is kind of you are implementing, you are adding to the algorithm a way to the algorithm to be close of your reality, of human reality. Once logic is a perfectly human construction. I mean, if it is well constructed, it leads to truth, right? To a logic truth. Yeah.
Well,
Cool.
one point here is, there is no perfect abstraction. It all depends on where you are coming from. But when you build a system, an inference system, it depends on your hypothesis, your premises, and the data that you have. But the key challenge that we have today is that those very large systems, in terms of for instance, large language models, you have huge amounts of data. And by huge amount of data, it's data that when you explain to people the amount of data, the number of lines, the number of words, the number of characters that those systems process, people, they get surprised. They didn't believe that a computer could process like basically, an amount of information that's unthinkable, right? And when you bring information from all over the web, texts that were produced by, literally millions of people, if not a billion people all over the world that are scrapping the web, and we don't know exactly where the data is coming from. Only the companies that build those systems know exactly where are the sources of their data. This is strategic information. Of course, they will not reveal something that's very sensitive, why my language model works better than your language model, or why model A works better than B and C. It depends on several technical issues, but it also depends on the data that you are acquired, the way that you process the data, the way that you label the data, the way that you curate the data that you have. And the thing here is that this massive amount of data, there are lots of contradictions, there are lots of biases, there are many, many, many errors in the data, there are wrong information. People write things on the web that is wrong. And when you have a system that operates in a statistical way of making inferences and drawing inferences from this data, if you are beginning from data that are biased, data that is biased, or you're getting that from data that has errors, technical errors, the output will be biased. The output will be, full of errors. The output will generate hallucinations when you get data from things that from sources that you haven't curated in a proper way. So that's why combining symbolic techniques, combining logic-based techniques in AI can provide a better way of designing such systems. And there is, even Stephen Wolfram, the guy who developed Mathematica, Wolfram Alpha and so on. He recently wrote a book on using ChatGPT and said that ChatGPT and the language models offer now an interesting way of interacting using symbolic language and the neural network approach. So he also sees the importance in his latest book of the combination of neurosymbolic, the combination of neurons and symbols towards neurosymbolic AI. So these hybrid neurosymbolic AI systems can be powerful and can be the way forward for safer artificial intelligence that provides, better results, that more control results with less biases, less errors, and even can perhaps be a solution for the problem of misinformation and disinformation on the web.
Yeah. Well, and this totally leads us to the next question, that would be, what is the best way to integrate the neural and symbolic architectures?
Well, there are many approaches. There is not one size fits all, right? When we say neurosymbolic AI, we say that it's a system where you use machine learning-based systems and you combine that with a symbolic-based approach. For instance, there are ways of developing systems that learn to reason about temporal information. Then you have to design the proper neural networks algorithms that are capable of drawing those temporal inferences, that can learn how to process information that evolves in time. So you have to teach the system and design algorithms to design the proper reasoning rules using artificial neural networks. It's like you are training a neural network to learn to reason, like you're training a neural network to do the logical inference that's typically done, let's say, in a theorem prover or in another symbolic system. This is one approach. Other approaches is like, when you're using a language model and you are interacting with this language model in prompt engineering, some people claim this is already a neurosymbolic integrative approach. Because why? Because when you are using symbolic language to interact with a neural system, obviously the symbolic interaction with the neural system is a neurosymbolic approach. So there is no one size fits all. The idea here is the general principle, is the general philosophy that when you have a system that is heavily based on machine learning, if you want to ensure certain properties of the system, like safety, like transparency or explainability, you have to find the best way of using a logic-based systems towards reaching those goals, towards integrating with those integrating those two approaches. And it's also interesting that when you look at industrial applications, several of the big tech companies are investing in neurosymbolic AI. Gartner has recently produced or published its hype cycle for artificial intelligence in 2023, and for the first time, they put in the innovation trigger in the hype cycle curve at the beginning of the innovation curve. They put some very interesting things over there, including neurosymbolic AI, including causal AI, and they see that neurosymbolic AI is something that is already in the innovation trigger. Of course, when you are in the innovation trigger of the life cycle of the hype cycle of Gartner, it means that the technology can take up to 10 years for industrial use or massive industrial use. But let me remind everyone, the deep learning revolution didn't start last year, didn't start with ChatGPT. The first paper that Geoff Hinton published that had the word deep learning or deep in the title was published in 2006 in a journal called Neurocomputation. And this paper was the first paper that he showed in 2006 in the Neurocomputation journal, that deep leaf nets were very effective for certain applications. And that was a paper, that only the academics knew, that only, let's say, the smaller research community at the time knew. So that was in 2006. By 2012, they got much more popular beyond the neurocomputation community, beyond the AI community, and the computer vision community. After they published a paper in 2012 in the conferences in computer vision and pattern recognition, the people in the computer vision field, they realized that neural networks could be the dominant approach in computer vision. And then the rest is history. Over the last 10 years, then people realized that neural networks could be applied in natural language processing, could be applied in many other applications. And today, everyone in AI is using artificial neural networks. So when we think about neurosymbolic AI, we say, well, we are just starting. Maybe some people say it's too early. Maybe some people say, well, I don't believe it's not going to work. But in 2006, very few people knew about this novel approach that Geoff Hinton had developed. That he built over his whole career, that he started in the 80s as a researcher. In the 80s, people got very excited about neural networks. Then in the 90s, the field faded away. Some of us stick to the field, kept doing research. Of course, Geoff Hinton is someone who has done over 40 years of research in artificial neural network learning. And by persisting working in this field, he showed that neural networks could be very effective. And in terms of neurosymbolic AI, we see, at some point, if AI is becoming, this general purpose technology, you need explanations, you need security, you need transparency, you need to understand the causes and effects of the system. And for that, you will need a symbolic approach combined with a neural network approach. And it may take 10 years, but 10 years go very fast. 10 years is like nothing in the history of the world.
Yes, it's just remember that the Attention is All You Need paper was published in 2016.
Yes.
And it was the beginning of the revolution of the transformers architecture.
Absolutely.
Speaking of transformers, by the way, can I say then that the self-attention module of the transformer architecture is implementing a neurosymbolic approach?
Well, if you're thinking in terms of inferences in language, or if you're trying to identify which words are more relevant to the others when you are in the end of the day using a transformer-based architecture or some transformation, what we can say is that yes, there is a reasoning component over there, but there is another thing that people don't realize sometimes. Any programming activity that we do is a symbolic. It's a symbolic way of.
That will be my next question, but
there is no programming language that's not symbolic. I haven't seen anyone programming anything on a computer over the last 30 years. It means that I'm not that young, not using a symbolic language. So the thing here is, the neurosymbolic approach is powerful. And the thing is that those neural network algorithms that come from a very simple idea in backpropagation, using the chain rule, and, of course, there are technical details that people change and evolve, the ways that they develop, embeddings, encoding things. But the basic idea of what's going on in a neural network, it stem out still from the first algorithms in the 70s and 80s. There have been changes. And the transformer model, some people showed, or many people showed, of course, many people showed, not some people, many people showed that they're very good at dealing with sequences, and that in the end of the day, that was very important to predict the next word in a sentence or the next fragment in a text, or identifying, relations between words and, contexts in clusterings of tokens and words. And I believe that other people are also working on using, many people are using transformers to work on symbolic mathematics or symbolic reasoning as well. So I believe that transformer is one of the architectures amongst many others that are amenable to a neurosymbolic approach.
Cool. Yeah. Cool. So Luis, we've been seeing a growing trend in multimodal architectures, right, in deep learning. And there are many types of neurosymbolic approaches, as you just mentioned. Is there a neurosymbolic approach that do you think might hold the promise of working as a multimodal neurosymbolic architecture? Do you think the integration of neurosymbolic can boost multimodal applications?
Yeah, that's another great question. Multimodality is not something new in computer science. It's not new even in logic, right? You have multimodal logics that have been developed over the last 50, 60 years, exactly because you are combining different modes of reasoning, different modes of expressing what's going on in the world. And here, of course, people are saying, wow, the multimodalities are connected to images, are connected to language, are connected to other dimensions. And the fact that we have shown how complex those systems become when you are building a logical system, or you're building a computational system that deals with language, that deals with images, that deals with movies, that deals with songs, and so on, shows that shows the need for using results that have been proved in the past that can help you developing more powerful systems. So using more powerful systems. So multimodalities, again, it's not something new in computer science. It's something that has been developed for many years in many different branches. And the fact that people have developed reasoning systems and reasoning tools for multimodalities is something that can help the development of multimodalities in the context of these new generative AI tools and techniques and technologies that are under development.
Okay, yeah, cool. So in your paper, you and Garcês' paper, the one AI third wave, in your symbolic AI third wave, you wrote something very interesting, and I quote, you said that that there has been proved that neural networks are capable of representing propositional logic, non-monotonic logic programming, propositional model logic, and fragments of first-order logic, but not full first-order or higher-order logic.
Mm-hmm.
Do you have a guess or something like what is needed to neural networks inside a neurosymbolic approach to represent full first-order logic, or even high-order logic?
Well, today when we are talking, these sentences in the paper, they are in the context of showing a mathematical proof or a mathematical construction that proves that you can, for instance, represent certain logics. But the fact here is that, first-order logic is undecidable. We don't have an algorithm. You don't have a computational mechanism that for any, full first-order logic system will be, sound and complete. It's a very technical idea.
Yeah.
Why do we say fragments? It means that for certain applications, and by fragments we mean a subset of this logic, we can, of course, use neural networks to learn to reason using this kind of logic, right? The point here is that first-order logic is undecidable, but we already have shown that neural networks can represent relations. Even the language models, even the applications that we have today, they represent relations in a very effective way. The thing that we're referring here was a mathematical proof for those results, right?
Yeah.
The fact that formally something is not complete, it doesn't mean that for subsets, it means a subset is always not the whole, right? Informally speaking here, a subset of certain constructions cannot be represented. And sometimes, fragments of certain constructions are enough to represent the knowledge about a given application. You don't need the full power of a certain logical system for everything that you are trying to process in a computer or in a computational system. So the idea here is that also it shows that there are research questions that should be further investigated, and also those questions can help building stronger AI systems, because as you learn to represent knowledge about the world, and as you represent complete knowledge about the world, that's very hard to do, and possibly and maybe it's not even possible, to have complete knowledge about the world in certain scenarios. You need better formalisms for that. You need to represent those formalizations. You need to develop, proper algorithms for that. And what we have shown, and what many people have shown in neurosymbolic AI, is that you can represent a variety of logical languages, a variety of logical systems, at least in terms of fragments of those systems, in terms of parts of those systems. If you cannot be sound and complete, as we have, as we have shown in symbolic systems, at least you can learn fragments of those systems, and you can represent knowledge that's expressed via the language of those classical logics or non-classical logics. That was the point that we want to try to make. It's possible to represent logic-based systems, but there is still a long way to go. Yeah, there is still a long way to go.
Okay, this is great. Yes, it's the answer, of course, is understandable. Yeah, this is great. I'll keep thinking about that in the next 10 days, by the way. Well, we have a question here from the audience, Alexandre Del Rey. He's asking, what are the main challenges of new applications in neurosymbolic AI at the moment? I think it was partly answered. What are the main challenges for neurosymbolic AI at the moment?
Yeah.
At the moment, in the advance of probabilistic approaches with deep learning models, he's asking if the challenges in a probabilistic framework if they are how they are actually.
Mm-hmm. Well, no, I mean, of course, he mentions that there is, advances in probabilistic approaches or statistical approaches. Yeah, of course, deep learning is based on probabilistic or statistical approaches. However, that's exactly, what leads to certain restrictions in the use of those approaches. As I mentioned in the beginning, for certain critical applications, as I mentioned, those applications, you need better results than the levels of uncertainty. They must be reduced to absolutely minimum. For certain applications, you cannot offer 95% guarantees or 97.5% or 99% guarantees that the system will work. So in this case, that's why people use, and people will keep using, symbolic, exact, deterministic approaches in computer science and in technology. Right? You want to make sure that when you take an airplane, when you take a flight, the flight will reach the destination. You want to make sure that your energy supply is going to work. So, of course, probabilistic approaches are very important, and there are probabilistic logics, there are probabilistic systems that represent nicely things about the world, and there are probabilistic logics that represent how uncertainty operates in the world, or how to deal with uncertainty in uncertain environments, right? Because for certain environments are non-deterministic by definition. We cannot make them deterministic, right? So those two worlds, the uncertain and certain worlds, that we're going to live with them forever, and there are risks in certain things. And for those approaches, for those systems where we have a lot of risk involved, we try to reduce the risk to a minimum. But in certain cases, in certain applications, the risk must be zero. That's why, you have to consider a spectrum of applications, how much tolerance you have to risk, what's the probability, what's the security level, what's the risk level that you are capable of manage. And in order to do that, you must have a set of tools to operate in different environments, and neurosymbolic approaches can be one of those methodologies to operate in certain environments.
That's interesting, right? So the uncertainty has to stay in the environment, but not in the decision making of the algorithm, that's very interesting.
Yeah, the environment can be uncertain, but you have to
Always.
be certain of the decisions that you are taking in this
Precisely.
environment to guarantee certain properties and characteristics of, the behavior of your system.
Yeah, exactly. So he has another question, and that one is hard. I think it's similar to a question that I just made. It was, what are the possible paths to incorporate the abstract thinking the solutions of AI, like generative AI. It's more
Well,
specific. It's more specific about
no,
generative AI.
it's a great question. If you think in terms of generative AI, and let's say, systems that are generating language or language applications, natural language or natural language understanding, language is already a symbolic expression. At least written language is already a symbolic expression of knowledge, right?
Exactly.
So the thing here is how to make those systems more precise, and also how to guarantee that those systems will not produce misinformation, will not produce disinformation, will not produce biases, conflicts. They will not be harmful to people. So in order to do that, for certain applications, you need rule-based systems that are combined with the neural systems, right? I call new rule-based systems or symbolic in neural systems. And I like the examples. Again, I will refer again to Wolfram. Wolfram said that the language models, they offer one of the interesting technological technologies or technological tools, which is redundancy. They offer some interesting technologies to combine symbolic reasoning and symbolic tools in AI with this deep learning approach, because language by definition is symbolic. Also, when you are dealing with the systems and you are expressing mathematical logic, in the end of the day, we will need to represent our knowledge on mathematics using a symbolic language. So the abstract and symbolic, they are already being combined with the neural connectionist statistical approach in a number of applications. And when people are interacting with a language model using prompt engineering or techniques to deal with this technology in a more effective way, the best way to extract knowledge, they are designing symbolic ways of using natural language to interact and extract the information. This is already a neurosymbolic application. So the smart way of developing prompt engineering or prompt programming or prompts is the smartest way of using the proper symbolic language to interact with those systems. So by definition, it's neurosymbolic.
Yes, cool. Guys, if you have more questions, please do it, okay? So, Luis, let's go to a bit of science fiction now. Do you think the neurosymbolic approach would be really fundamental to AGI, whatever that means?
Well, we are building, AGI, artificial general intelligence, where there are many definitions, but when we reach a point in history where the machines will be as smart as we are, of course, if we want very smart machines, we can imagine that, wow, those machines will be the best mathematician in the world, or these machines will be the best writer in the world, and these machines will be maybe the best athletes in the world. So so there are many challenges before we get to there. Only the embodiment problem, like transforming those machines into a robot, into a cyborg that will be walking with us, that's a huge technological problem.
Oh, yes.
We are many years away from that, from having a Terminator scenario or from having a negative scenario. I believe that we have challenges ahead that are much more connected with producing wrong information, with misguiding people, with producing disinformation, with leading to biases, and maybe with all this misinformation leading to misunderstanding amongst people. So all these things have to be solved way before we move towards AGI. And I don't believe that only a single technique, only large language models can lead to AGI, because they are connected much more to natural language processing and producing text and summarization and information about what is expressed in terms of a specific kind of data. That's data that expresses our language. So expresses human language. So we are still, further away from AGI because the complexity of building technology and, when you build technology in your life, you know how hard it is. So when I think in terms of what we need towards AGI, in terms of combining different technologies to build something that reaches or approaches AGI, I think, wow, this is still very far away, very, very far away. We will have systems that are very good at, well, it's very interesting to analyze certain kinds of text, or it's very interesting, to generate some business models, or it's very interesting in terms of producing interesting movies, images, virtual reality, and so on. But we are very, very far away from AGI at this point in history because the complexity of building technology, people, who don't work in technology building, they don't realize how hard it is to build, let's say, the single hand of a robot. They don't realize how hard it is to coordinate the fingers in the hand of a robot, how it is hard to build a vision system that works together with a language system and moves an arm and, walks around the environment in a way that's meaningful. It's extremely hard to build that. It's so hard that nobody has done that yet. So we are still a bit far away from that.
Yeah. Well, as a neuroscientist, I tend to, in the past, I tend to think that the integration of symbolic paradigm to neural networks is kind of the distancing of deep learning from the already few brain-inspired traces it has. So it seemed to me a step back from the connectionism realm. But now I have to say, especially after reading some of your papers and during this talk, I have to say that I kind of changed my mind, because when you consider natural neural networks, of course, it is not, you don't have symbols getting into the brain, getting into the brain or getting out of the brain. But all the abstraction that we make, our contact with other people with the world, it's based on logic, some sort of higher order logic. So I have to say that I changed my mind. Actually, with the symbolic approach with neural networks, we're not distancing deep learning from a brain inspired. Maybe we are getting closer. Maybe we're getting closer. So this is very interesting. Luis,
yes.
What are the next steps in symbolic AI? What do you think?
Thank you. Sorry?
What are the next steps in neurosymbolic AI? Can you hear me now?
What we are seeing at the moment is 20 years ago, when we are combining logic and neural networks, people say, why? Why are you doing that? So at 20 years ago,
I thought about that.
20 years ago, people said, why neural networks and logic? I couldn't see why not, because to me, the higher forms of reasoning, like producing sound reasoning, explainable reasoning, and producing results that are safe, secure, transparent, and explainable, was always my aim as a researcher for the last 25 years. So, and when I saw how neural networks were deployed, you have very interesting applications in vision and language and translation and so on, but you couldn't explain anything. You couldn't explain the inference process. So to me, it's very natural that we bring together the best techniques from logic-based AI or from computational logic and integrate them with neural networks and machine learning. So learning to reason in a proper way, or machine learning to reason in a proper way, in a safe, security, explainable, transparent way, to me is one of the key aims of artificial intelligence, one of the key aims of science, because AI is everywhere. And, our lives as a species on the planet, we evolved as we learn to reason in a sound way, and you do experiments that show that certain things work, and so that we produce better technology and technology that improve the quality of life in the planet. So in order to have richer technological models, we must bring together different techniques. And to me, it was very natural. And today, some people realize that it was not an idea that, it was an idea that made sense. And many people are investing now on combining, the neural approach and the symbolic approach in neurosymbolic AI systems. And that's something that makes me very happy. We are not that wrong 20 years ago.
Yes, that's cool. That's really great. Well, that would be my last question, but we have time for one more, just one more, guys. Do you think, of course, logic is kind of a framework with a very closed form. Do you think that the neurosymbolic approach could maybe open questions for logic itself? I mean, maybe ways to even increase logic if it is possible?
Absolutely. You can feedback, you can learn. When we use neural networks to express logical reasoning, even the logician said, why are you using a neural network? And then we explained to them, wow, we want to develop algorithms that can draw inferences using a neural model. So our computer is not the typical computer. Our computer is the neural network. So the inference system is based on how the neural network computes that information, computes the premises, generate results from the premises and the hypothesis. And then people realize, oh, yeah, it makes sense. And today, people are very excited about, learning what kinds of logic can be represented in neural networks, how to verify the results of a neural network. So this leads to a lot of interesting results that from a computational point of view, the logic community is coming back to analyze what these guys were doing 20 years ago, and they are rediscovering a lot of things that we were doing 10, 20 years ago, which makes me, even happier. It's coming from both the neural networks community, the machine learning community, and also from the computational logic community. People got interested in the field. Yeah.
Yes, you know what? Just for you to know, in my community here, professors here around me in the postgraduate courses, I became kind of the neuroscience with the logic thing because of your papers, by the way.
Thank you. No, let's stay in touch. I'm very happy to talk to you and your friends. Yeah.
Cool. And be aware, after this lecture, in the next days, I will make more questions to you, okay?
No, thank you. Let's stay in touch.
Okay.
Yes.
Guys, do you have more questions? Wagner is coming in. Luis, thank you so much. I would stay easily for more 2 hours. Thank you very much.
Thank you.
Thank you, guys. Thank you, guys. Thank you so very much. It was very, very enlightening for me, especially to realize I'm actually doing neurosymbolic AI with the chain of thoughts, tree of thoughts, some techniques that we are applying are already being used to leverage large language models and as well as neural networks. It was a fascinating conversation. Thank you so much, Bruno and Luis. I will switch to português. Então, pessoal, teremos então hoje às 7h30 a mesa redonda, onde iremos discutir os temas que foram na própria entrevista e os temas que foram discutidos, que encerra o nosso I2AI Experience. Então, novamente, obrigado, professores Luiz e Bruno, e nos vemos